Hello everyone, I'm Miga and welcome to my channel. So today we'll be doing some practice identifying isomers. I hope you've watched my previous video when I detail the difference between constitutional isomers, stereoisomers, etc. And here I want us to actually do some practice just like a regular question you would get on your exam. Suppose the professor give you the following compound and they ask you to determine the relationship between those two structures, right? Remember, for isomers, to even be in the world of isomers, we need to make sure that we have the same molecular formula. First and foremost, let's check if they have the same molecular formula. After counting my amount of carbon and hydrogen, I can confidently say that they have the same molecular formula. So yes, we are in the world of isomers. Now, to determine what type of isomers, I first focus on the name. If these two compounds have different name, then I know they would be constitutional isomers. That means their connection was different. Something was different, whether the functional group or the position of the functional group or different in their connectivity, then I know we're talking about isomers. So let's see that. After determining the full name of each compound, I can see that indeed the name are different for each structure. Like the structure, they don't have the same name, then they are constitutional isomers. And when I say this, everything doesn't have to be different to say that they are constitutional isomers. For example, here the backbone by itself is already, like, for example, you could have ignored this, the substituent, and quickly analyze the backbone. If the backbone are different, then the compound is the constitutional isomers if they have the same molecular formula, okay? And with that, let's speed up a little so that we don't make this video too long. Here, try to do it, and in a few seconds, I'm gonna reveal the answer. What do you think? Are they constitutional isomers or not? And here, guys, quickly, I determine the molecular formula for each. Yes, to save time, I don't want to write hydrogen everywhere, guys. So my red mean hydrogen, my red sticks mean hydrogen, right? So I can see in both cases, we have indeed the same molecular formula. These are the same. C5, 5 carbon and H and 11 hydrogen for both structure. So now, but look at this guy. Here, if I were to number my carbon, 1, 2, 3, I would say here we have a 3 bromo, right? Meanwhile, on the other one, 1, 2, we have 2 bromo. Remember, guys, in terms of numbering, we need to give any substituent the lowest carbon position. That's why I started to do it this way. So 2 bromo, here alone, I can already tell that, yes, they have the same molecular formula, but no matter what their backbone will be, we are in, these will have different name. So these are also constitutional isomers. Let's do, and here is a nice example that looks pretty fun where we can actually put together everything we talk about stereoisomers. So first, I hope you can see like me that these two structures look very similar in terms of connectivity. So probably the name, the molecular formula is gonna be the same, but it's always good to check. After adding all the hydrogen and after counting the hydrogen and carbon, I noticed that both have the same molecular formula. And even the name, I tried to name each of them, and I see that they have quite similar name. So two things can happen, guys. If this compound have the same chiral center, because I'm noticing some chiral center here, if the chiral centers are identical, then these two will be identical compound. But if the chiral centers are different for both compound, then we talk about stereoisomers. For example, what I mean by that is that if here we have A, S, the other one is also A and S, assuming that we start numbering this way, 1 and 2, 1 and 2, both should have the same chiral center, then they will be identical. But now, guys, if the chiral center differs, we know that we'll be in the world of stereoisomers. Now, even for stereoisomers, we can have, they can be either enantiomers or diastereomers. Now, let me remove this. I think you get the idea of numbering. If, for example, we have A and S for one structure, and the other one is the perfect opposite, SR, then we talk about enantiomers. They are mirror image of each other, okay? Enantiomers. However, if one is S, the other one is RR, they are not perfect opposite, then we will talk about diastereomer. So before we come up to a conclusion about the pairs, what type of stereoisomers, or even if they are stereoisomers, let's determine the chiral center. In this video, I'm not gonna show how to determine R or S configuration. I think it could be a good idea to watch my previous video for that. So let's quickly determine the chiral center, and it's a good practice for you. Let's do it together. Quickly, to determine the chiral center of this carbon here, I'm going to assign some priority to the 4 different groups my carbon is attached to. Hydrogen is always have the lowest priority, so I'm going to put a number 4 next to it. CH3 usually is always second to the lowest, so it will be number 3. Now, I'm going to determine which one between these two pathways here have the highest priority. I know that this carbon is attached to 2 carbon and 1 hydrogen. We know that one is attached to 1 carbon and 2 hydrogen. So I agree that this one will be 1 and that one will be 2. Now, guys, quickly, I'm going to check to see if my hydrogen, the lowest priority, should be on the dash and the highest priority should be on the wedge. And since we don't have that here, yes, my lowest priority is on the dash, but I want number 1 to be on the wedge. So what I did is I recreated my structure here so that I can flip twice, okay? Or my numbers, let's say my group, I'm gonna flip them twice until I can get the structure that I want. First, you see that this is very identical to this. Number 3 is on the wedge, 4 is on the dash here, and I've added the other group. I'm gonna do I did my first flip between 1 and 3, okay? And then my second flip between 2 and 3. So that now I have, let me remove this for a second. I have number 1 on the wedge and number 4 on the dash. Now we're ready to determine if the numbering is clockwise or counterclockwise. So I'm gonna go 1 to 2 to 3, and I'm seeing that it's clockwise. Then it's a configuration. Let's put a nice R here. Since we're done with this one, let's remove the color so that we can do the other chiral center, which is this one here. After determining the chiral center, the configuration of each chiral center, we notice that we have perfect opposite, right? Which means that we're talking about mirror image. So we can say these two structures are enantiomers. Enantiomers, to remind you, have the same molecular formula, thus the same name, right? The only thing that differs is the spatial arrangement of the atom. So that means their connectivity is quite the same, but the way for example, substituent or attached on that backbone is different. So in that case, since we have perfect opposite chiral center, we talk about enantiomers, which is a type of stereoisomers. Now let's do another example. Now let's push the concept a little bit further. The professor can also give you 2-chair conformation, guys. Again, same idea. Remember, we can represent the structures in different way. There's a Newman projection, there's a chair. So let's do for this one, these 2 chairs. Same thing. Let's see here. I hope you can tell that the molecular formula will also be the same. Let's look. Would we have the same name? Okay, I can see that we have the backbone here, both the backbone will be a cyclohexane. I'm putting this just so that I can, it's my way to tell that, hey, you haven't done anything, you just name the backbone. Okay, so now let's analyze the location. Location of substituent can give it away sometime. So if I were to start counting here, so we have 1, 2, 3. So this one will be 3, 1, 3. Oh, I can remove this now. Dimethyl. Cyclohexane. What about this one? If we study the number here, 1, 2. Oh, I can already tell that the names are different. Here we have 1, 2, dimethyl cyclohexane. Name are different, so these two will be constitutional. I know it's not pretty, guys, but hey, isomers, okay? Because let's say the professor gives you these two compounds. Remember that you can convert this structure into the cyclic form too. Okay, so they are the same thing, especially the backbone. We have 1, 2, 3, 4, 5, 6. Here we also have 1, 2, 3, 4, 5, 6 here. Again, we can place, it's the same thing. Actually, if you watch my the how to build the chair conformation video, you'll see that when I put a light through this, right, and I realized that the shadow was actually a cyclic cyclohexane. You can take a look, it's pretty cool. But let's go back to what's trying to say. First, let's determine if they both have the same molecular formula. Both have the same molecular formula. Indeed, we can already tell that we're gonna have an isomers, right? Isomers were in the same word. Oh, sorry, I put this one, C8. Okay. And now let's see. We can tell, let's convert this chair into the cyclohexane structure. We already know, let me highlight in yellow the backbone. This is the backbone. This is the same as this one. Okay, same one. Now let's place the substituent. I like to start numbering my carbon at this position. So 1, 2. Here at position 1, I can see that my methyl group is pointing down. And at position 2, my methyl group is pointing up. I'm going to do the same thing and make sure that if I number 1 and 2, oh no, let's follow the same pattern that we saw here, right? 1 and 2, at position 1, my methyl group will be pointing down. And at position 2, my methyl groups should be pointing up. Now I can compare those two structures, right? I've just named them. I just put the numbering so that it's even clearer for you guys. Oh, here, sorry. Now we can compare these two, and what do we notice? Like I said before, if you see there's a cyclic component, remember that we cannot rotate these substituents to interconvert them. You can't just rotate this and say that we're gonna convert it into, like, put in the down position. So here at position 1, the methyl group is pointing down, and at position 2, the methyl group is pointing up. However, on the first structure, position 1, both methyl group are pointing up. They are both stuck in this conformation. You cannot interconvert them. They are still isomers. And that's all I have for today. I hope I gave enough example to give you a feel of how your question will be asked on the exam, okay? So remember, it's all about practice. You got this. Keep practicing until you get comfortable with the material so that we can move on together to the next topic. So thank you again. See you on the next video.